right, with the same set of matrices, how do I reduce this irreducible representation? Hey, don't talk. Okay. To do that, to learn how to do it, first of all, we have said that you can do similarity transformation and all that, but then it's very difficult to find out exactly which matrices we are going to use to perform the similarity transformation. So today we will learn a very simple formula, very simple relationship, which will let us decompose reducible representations into the constituent irreducible representations. Alright, we are going to use great orthogonality theorem for that. So, great orthogonality theorem, character table, these things, well, great orthogonality theorem deals with everything, but then we are going to use the character table also. So, let us find the characters of these matrices. What are the characters of the matrices? What are the operations? E, C2, sigma V dashed. So, what is chi r? Tell me for this representation. What is chi r for this representation? Chi r for E for this representation, what is it? 2? 1 plus 1, 2. I am just writing this down, I will show you in a minute. What is chi r for C2? 0. What is chi r for sigma V? 0 or 2? Do not get carried away. Add and give me the answer. 2. What is chi r for sigma V dash? 0. Alright. This is what it is. Right? 2, 0, 2, 0. Now, we are going to learn how to decompose this representation into its constituent representations, constituent irreducible representations, and we will do it fairly easily. So, see, this is a reducible representation, fine. Now, as you told me correctly, it is not block factorized, but as we also discussed, it is possible to block factorize it by performing some suitable similarity transformation, right. So, what I can do is, let us say these matrices are D matrices. I can perform some kind of a similarity transformation, I do not know what X is, to get these D dash matrices which are block factorized. Okay. I do not know what they are, but then if I block factorize, I can write down the matrices that I will get. Can I write down the matrices that I will get if I block factorize? Can I write down the matrices that I get? No. What can I write down? You have started with these 4 matrices whose characters are 2, 0, 2, 0. I have performed the same similarity transformation on all these 4 matrices of this representation, and I have got another representation consisting of D dash matrices. What can I say about these D dash matrices? Okay, let us see. We can say 2, 3 things. First is that this representation will also be a 2-dimensional, right? What else can I say? Yes, they are going to be block factorized. That means they are going to be all diagonal matrices. Correct. What else? Which is another way of saying that it is going to be, they are going to be all diagonal matrices. Try to think, this is something we have discussed earlier in class. We have derived. Same traces, right? Same traces, right? So, even for D dash star, the characters are going to be 2, 0, 2, 0. Remember, if I perform a similarity transformation, the conjugates have the same traces. We have proved that earlier, isn't it? At that time we had said that matrices in the same class have the same traces, but then after all matrices in the same class are nothing but conjugate to each other, they are similarity transformations of each other. So, no matter what similarity transform I perform, the trace is not going to change, the character is not going to change. I hope you have not forgotten what is trace, what is character, right. Okay, everybody comfortable with that? So, I think we all agree that even though I have performed this similarity transformation, whereas these matrices have become diagonal matrices, there is no reason why the traces will change. The traces are still 2 0 2 0, I can still work with these same traces 2 0 2 0. Okay? Okay. Now let me write this. Now if you have block factorized matrices, then will you allow me to write things like this: chi r, chi of r is the character of the transformation matrix corresponding to R in the reducible representation. This is for, I will just write RR. RR means reducible representation. These are the characters of the reducible representation. Will you allow me to write that chi of R is equal to sum over AJ chi j r, sum over j AJ chi j r. A is the coefficient, the question is what is j? J is the number of blocks. Let us say this is a block diagonalized matrix. Right. So, for this block j is equal to 1, for this j equal to 2, for this j equal to 3, alright. And for each block I can get the chi's. So, this is chi 1 r, this is chi 2 r, making a mess of it, this is chi 3 r, got it. What are these blocks? These blocks are the matrices of the constituent irreducible representations. Remember, we had written something like this: gamma equal to gamma 1 plus gamma 2 plus gamma 3, so on. Block addition, we had done block addition, where the subscripts 1, 2, 3 are the different blocks. What I am saying is I am working out the characters of each block for each matrix: chi 1 r, chi 2 r, chi 3 r, and it is possible that we have some degeneracy, some blocks are same. That is why we had written, we had written this equation like this also, right? Sum over j aj gamma j. So, chi is just the character corresponding to each operation in the jth block. Are you okay with this? Are you okay if I write it like this? Chi of r equal to sum over j aj chi j of r. Okay? The character of symmetry operation R in the reducible representation is a weighted sum of the characters of all the constituent irreducible representations. What is that? Aj is the coefficient. So, we have written Aj here also. The point is, it is basically gamma 1 plus gamma 2 plus gamma 3 plus gamma 4. Sometimes it may be possible that gamma 2 equal to gamma 4. So, it does not make sense writing gamma 2 gamma 4 separately. I will just write 2 gamma 2. J is the number of blocks, right. So, number of distinct blocks. So, if these are irreducible representations, they will be distinct. That is right. Okay. You can go ahead. Just write it again. chi of r equal to sum over j aj chi j of r. What can I do now? What do I want to do? I want to break it down into constituent representations. Okay. So, one thing I can do is, let us write multiplied by say chi I r, where I is one of the j's. I is a specific value of j. So, I can be 1, 2, 3, whatever it is. Okay. Will be equal to sum over j aj chi j of r multiplied by chi I of r. What should I do next to simplify the right hand side? We are dealing with irreducible representations. Right hand side only has the irreducible representation, right? So, what is the relationship between the chi's? Yes, delta ij means what happens if I sum over all the symmetry operations, then that Kronecker delta will come, right? So, what I can do is, on left hand side let us say sum over r, or right hand side also we will put sum over r. Alright. So, I can perhaps write it like this. So, what will the right hand side simplify into? Sum over r, sum over j. So, what should I do next? What does rate orthogonality theorem tell us? Does it not say sum over r chi I of r chi j of r equal to delta ij? Is this not a consequence of do not insert an a before the t? What happens if you insert an a before the t? Instead of a theorem, you get an animal, right? So, great orthogonality theorem tells us this, right? Right or wrong? Right, isn't it? So, what I will do is I will just put it like this, sum over j, let us say aj, then sum over r chi j r chi I r this is not delta ij. What is this? H delta ij. Don't forget that. Okay, H delta ij. Now, so what do I get? What does the right hand side become? See, which one is the specific value? I is a specific value. J is the variable. Okay, so J is going to go from 1, 2, 3, 4, 5, 6, and I is something. So, what are the terms that will survive? Only chi I of r. Only that will survive. Which coefficient will survive? Only ai, right? So, will you allow me to write it like this? ai into h, right? That is a nice relation. So, what is ai then? 1 by h sum over r, left hand side has not changed, chi of r chi I r. Okay. So, this is a relationship that I want you to remember. Even if I barge into your room in the middle of the day, wake you up, I did not say night, day, wake you up and ask you what the relationship is. Alright. will use this very frequently. So what does it mean? That means the coefficient is 1 by h sum over r chi of r chi I r. Then what do? You have these 4 chi's, right? 2, 0, 2, 0. You take each, multiply it by the character that you have for whichever irreducible representation you are dealing with, right? And sum over all r's. All right. So let us see. Which point group is this? C2V. Visible? Yeah. Yes. Yeah. Do not forget that we have a class on Thursday at 5 p.m. For those who came late, we have class on Thursday at 5 p.m. No class on Friday. Then again class on Monday, Tuesday and Thursday next week at 5 p.m. Week after that we have class at 5 p.m. on Monday. I'll give you some puja homework. Durga Puja is there from that time. Yeah, of course you'll get puja holiday. We have 6 days of holiday this week, this year I think. Okay. Do we have character table with us? I do. So what you do is you please, let me write the relationship first. AI equal to, visible right, 1 by h sum over r chi of r chi I of r. Okay. And let me also write down what was chi e in our reducible representation. What was chi e? Chi of e? 2. What was chi of C2? 0. Chi of sigma v? Chi of sigma v? 2. Chi of sigma v dashed? 0. Right? Now I will show you the character table. Here it is. Can you read? Yes or no? Even if you cannot read. You know the first line at least, right? First symmetry species, A1. What are the characters? What are the chi i's for A1? 1, 1, 1, 1. Totally symmetric representation, right? So what I can do is I can just try to see what is the coefficient of, I can write it like A1. I could also write A, just small a1, just to make it more obvious, will be equal to, what is h? 4, everybody is convinced, h is 4, multiplied by chi of e is 2, multiplied by chi I of e is 1, right, plus chi of C2 is 0, multiplied by chi I of C2 is 1, plus chi of sigma v is 0, why so few and why so late, multiplied by chi I of sigma v is 1, plus chi sigma v dashed is multiplied by chi I sigma v dashed is minus 1. 1. What is the answer? What is the answer? Very difficult simplification. Even my 10-year-old son can do this. 1. All right. So, what is the next one? A2, right? What are the characters of A2? Even if I don't show you, you should be able to tell me. 1, 1, minus 1, minus 1. Very good. So now let's work this out. A2 will be equal to 1/4 2 multiplied by 1 plus 0 multiplied by 1 plus 2 multiplied by minus 1 plus 0 multiplied by, doesn't matter. What is the answer? 0. Okay. B1, even if I don't show you, you should be able to tell me. 1/4. What is it? 1 minus 1? 1 minus 1, 1 minus 1. Very good. So 2 multiplied by 1 plus 0 multiplied by minus 1 plus 2 multiplied by 1 plus 0 multiplied by minus 1 is equal to 1. Is there any need to work out A, B2? Is there any need for me to work out A, B2? There isn't. Because see, your reducible representation was 2-dimensional. You have already found that that representation is a sum of two one-dimensional representation. So the fourth representation cannot have any contribution. Still, if you want, you can work it out since you are doing it for the first time. What is B2? 1 minus 1? 1 minus 1 minus 1, 1. Work it out. What is A, B2? Zero. So, will you allow me to write that gamma is equal to A1 plus B1. A1 plus B1. All right. So, what have we learned? We have finally learned how to decompose a reducible representation into its constituent irreducible representations. And you see, we don't have to do any complicated mathematics anymore. We don't have to do similarity transformation, we don't have to even remember unitary transformation, nothing. All we need to do is, all that complicated math has given us this wonderful equation. That's why it's called great orthogonality theorem. This is the greatness. You can use it and you can decompose any reducible representation into its constituent irreducible representations.
It should have 4 irreducible representations.
Not necessarily. Why do you say 4? I'm sorry?
There are 4 classes.
4 classes, yes.
So there should be 4 irreducible.
Oh, no, you are talking about the character table. I am not saying that. See, what you are saying is, what should the character table look like? That we know already, that the character table should have 4. But now here what I have done is, I have given you 4 matrices which make up one reducible representation.
And when we started to work out with the C2V and taken oxygen and hydrogen atoms as basis, we got 2 types of matrices. One 1 by 1, that is the A1, and one 2 by 2.
Exactly.
So from that 1 2 by 2 set of matrices,
Yeah.
you have to get 3 1 by 1 matrices.
No. You cannot get 3 1 by 1 matrices. Why do you have to get 3?
There should be total 4 1 by 1 matrices.
No, not necessarily. It depends on the dimensionality of your basis. The dimensionality of the basis will determine the dimensionality of the representation.
But that should not change the character table.
It is not changing the character table. We are using the character table to find out what are the constituents of the reducible representation. We are not trying to write the character table again. Understand? Character table, of course, that we have worked out already. But while working out the character table, did we work it out with basis? With basis? No. Right? We worked it out using great orthogonality theorem. So that is part 1 of the story. That is done. Now, knowing that part 1 of the story, what we are trying to do is, now we have generated some reducible representation using some basis of our choice. It is not necessary that the dimensionality of the basis of our choice has to be the order of the group. It has to be less than the order. It can actually, as you will see in the next example, it can be more than the order of the group also. It can be anything. Now you want to break it up into its constituents. That is all. No, you won't. You will get the number of bases, the sum of whose dimensionalities should be equal to the number of elements in the bases. See what has happened, you have taken x, y, z, you got one dimensional representation earlier, and this one we have decomposed into two one dimensional representation, right. So 1 plus 1 plus 1, 3, and the dimensionality of your basis was also 3.
This is when we took like oxygen and hydrogen. When we took OH, X, Y, Z, we got one by one matrices.
What was that?
When we took X, Y, Z as basis,
Ah.
we got the 4 represented.
How will you get 4? Because the thing is, your matrix will always be 3 by 3. No, if you take x, y, z, you cannot get 4 by 4 matrix, isn't it? We had got 3 by 3 matrices. We did not get 4 by 4 matrices. The good thing about technology is that everything is here. Okay. So this is the basis we worked with. Hold on a minute. See. We got 3, right? We did not get all 4. Okay, convinced? But that is an important point that Orko has made, that the dimensionality of the reducible representation has to be the same as the dimensionality of the basis you use, and it also has to be the same as the linear sum or weighted sum of the dimensionalities of the constituent irreducible representation. Are we all okay now? If there is a question, please ask before we move ahead. So what I was saying is that if you have a basis, right, 3 dimensional, 4 dimensional, let us say I have a 5 dimensional basis. So if I have a 5 dimensional basis, can I have a 5 dimensional basis? Can you think of an example? Yes, you say 5, a chemist would think d orbitals naturally. So I can use these d orbitals as my basis. So I have a 5 dimensional basis. That means all the matrices I generate from there, the transformation matrices, they will be all 5 by 5 matrices, right. So this reducible representation that I get by taking a combination of these transformation matrices, that reducible representation is going to have a dimensionality of 5, right. So what I am saying is, now suppose you are able to break it up into 2 sets of matrices, okay, 2 irreducible representations. Then I am saying that suppose gamma 1 and gamma 2, 2 irreducible representations are there, then the dimensionality of gamma 1 and dimensionality of gamma 2 should also add up to 5. And d orbitals is a good example, and that is why I took 3 and 2, because in an octahedral field, you know, the d orbitals get split into 2 groups, as you know. What are the groups? T2g and EG. Now that you know the nomenclature, tell me what is EG, what will be the dimensionality of EG? 2. What will be the dimensionality of T2g? 3. What is 2 plus 3? 5. So that is what I was talking about. Okay, makes sense? There will be many repetitions.
At least 1.
Yes. But even if it is not more than the order of the group, you can have repetitions.
Yeah, but if it is more,
No, it has to be,